name is Yiming. Today I'll talk about our search for convergent evidence from TF binding locations and TF perturbation responses. So our main interest is to map the transcription factor networks. So in transcription factor networks, there are interactions that represent the interactions between the TF and their target genes. So we reason that the edges indicates that the TF binds to regulatory DNA of the targets. Therefore, such binding affects the transcription rate of the targets. And we call those edges direct and functional regulation. There are many approaches to map TF networks. One approach is to rely on TF binding location data from assays such as ChIP-ChIP, ChIP-seq, ChIP-exo, and transposon calling cards. Another way to map the TF network is to use the transcriptomic response after you perturb the TF. So these perturbation can come from you knock out the TF, you knock down the TF, you do CRISPR interference on the TF encoding genes, and also you could also induce the TF. In addition, there have been computational approaches to map TF networks from gene expression data. We know from previous DREAM challenges, there are algorithms such as Gene3, Inferlator, and recent development of Merlin and NetProfit also show promise to map TF network. So let's think about it. If most of the genes that are bound by the transcription factor is also responding to the perturbation of the transcription factor, then we would say the binding location data is sufficient to map the network. However, that's not what we observe. So taking yeast, for example, we analyzed the TF binding location data from ChIP-ChIP and TF knockout. And this is across 145 yeast TFs. All the numbers shown here are the median numbers of the response and the bond genes. The median fraction of the bond genes that are also responsive is actually very small, less than 20%. We did the similar analysis on human cell lines K562, where we're comparing the TF binding locations using ChIP-seq and the TF perturbation response data from TF knockdown. The median fraction of the bond genes that are responsive is even smaller, less than 1%. So here's our reasoning. Even we observed that in those these intersections are already very small, but we still think there might be indirect targets. The targets that are not direct and functional in this intersection. Here's our reasoning. So genes that are bound and responsive are not necessarily just responsive because they're bound. Because we know that many of the responsive genes are indirect targets and many of the TF binding sites are non-functional. So some of the indirect targets are expected to have non-functional binding sites. In other words, the bond and responsive genes may not be direct functional targets. As we did the analysis before, we can simply take the intersection of the two data sets where we can say that all genes that are in the intersection of the bond and responsive intersection are direct functional targets. So we derive a formula for the expected lower bound on the false discovery rate of this intersection methods as a function of 4 parameters: the sensitivity of the intersection methods, the number of bond genes, the number of responsive genes, and the number of genes that are both bond and responsive. As the latter 3 are measured by the experiment, the expectation of the FDR lower bound is simply monotonically increasing as the sensitivity increases. So we apply the formula to one example showing here is transcription factor GLN3, where we're comparing the TF binding locations and the TF perturbation response data. And what we're plotting is the relationship between the sensitivity and the minimum expected FDR, where the red line is the FDR lower bound as a function of sensitivity. With this data on this transcription factor particularly, we cannot achieve both high sensitivity and low FDR lower bound. So therefore, we come up with 2 criteria to argue that if a gene, if a TF is showing convergent evidence from both data sets, one, the FDR lower bound has to be 20% at sensitivity of 80%. And also the bond and responsive overlap between the two data sets should be expected more by chance. So we think this criteria is already very liberal. So any intersection that actually fill this criteria should not be showing convergent evidence. So we apply the criteria on the intersection method that we said before. This is analyzing 3 different comparison groups where we're comparing 1 in yeast and 2 in the human cell lines. And we show that less than 20% of the TF show convergent evidence in any of this group. So one way that we think could potentially improve is instead of using the TF knockout data, because that measures the steady states, which includes many indirect response due to the TF perturbation. With the more recent development, ZEV system can rapidly induce the expression of the transcription factor so that there's no time, so that you can measure the transcriptomic response shortly after you induce the TF. So most of the responsive genes are therefore enriched for the direct targets because there's no time for the non-indirect targets to respond. So we did a similar analysis. Instead of using TF knockout data, we're using ZEV data and compare that with the chip data. We show that the fraction of the TFs that show acceptable convergence increases. And then we seek to further improve our results because previously we're setting the thresholds on the TF binding location data and the TF perturbation response data separately. But there should be a way, because we have information for both, we should be smart about choosing the thresholds on both data sets together. Therefore, we're presenting dual threshold optimization. It's a method to, with a goal to optimize the overlap hypergeometric statistics. So what it does is simply tries out different pairs of thresholds from both data sets until it finds optimal threshold pair that maximize the hypergeometric statistic. We still require the same criteria as we showed before, the FDR lower bound. And here, the second criteria should be the optimized overlap should be greater than expected by chance. This is done through a null model generation through random signal simulation. So therefore, subsequently, we applied the dual threshold optimization to the two comparison group that we previously analyzed. And we showed that comparing the TF binding location from chip and TF knockout, we're able to improve from 19 to 30% of the TF that shows acceptable convergence. With the ZEV, we also observed a similar pattern. In addition, we have to note that the agreement between the two response data also increases. So to even further improve our improve our confidence on mapping TF networks from both TF binding locations and TF response data, we seek to further process the response data through network inference. So the reason why we're using network inference is that it's capable of utilizing information from many different perturbation conditions rather than a single TF perturbation condition. So the output of the network is the edge score for each TF to target interaction. And we're simply replacing the original response signal with the updated edge score. And then we compared the processed responsive data with the original TF binding location data and process that through TF dual threshold optimization. And here's what we got. So for yeast, we show improvement by processing using network inference. In this particular example, we're showing net profit 2 that improved the results over the unprocessed response data. And we show even stronger improvement when we process data on human, the responsive data in human, and the increases even further. We also try instead of using net profit as our network inference, we use other TF network inference methods that I mentioned before. They all seem to improve the result. So to even further improve our result, the last point I want to talk about is that there have been development in newer TF binding location assays, such as transposon calling cards and ChIP-XO. So in transposon calling cards, we're analyzing 12 transcription factors that are available in ChIP calling cards and also the 2 response data. So using the TF knockout data, we show that transposon calling cards is outcompeting the ChIP. ZEV improved both results, but still with transposon calling cards being the better performance. And also by processing the gene response data using net profit, we are able to achieve a high percentage or perfect percentage of the fraction of the transcription factor that show convergent evidence. With the similar analysis on 20 TFs that are available in the 4 data sets, instead of using calling cards that we use ChIP-XO, the trend is very similar. So this is very exciting because we're able to improve our network confidence, and this confidence comes with greater functional coherence. So what I'm showing here is that I analyze the output of the network from 2 methods, the intersection methods that use the ChIP and the TF knockout, and also intersecting the overlap between the TF binding locations from ChIP and the network inference process data from the 2 response sets using DTO. So what I'm plotting here is that for each transcription factor, I'm showing the best go term that are enriched for each transcription factor. The height of the bar represents the negative log p-value of the enrichment, and the number here indicates how many target genes that are associated with each go term. So in general, we observe that we're able to achieve more high confidence network that are showing much stronger go enrichment. Also, this covers many more appropriate target genes. So in our journey to search for convergent evidence from TF binding location data and TF perturbation response data, we started by defining 2 criteria for TF to be acceptable or show acceptable convergence. One is that FDR lower bound of 20% at sensitivity of 80%. And second, we require the overlap of the bound set and the responsive set should be statistically significant. And we're able to improve our results by first incorporating newer response data from ZEV system and develop a new methods to choose the thresholds called dual threshold optimization from both TF binding location data and TF perturbation response data. And also we seek to use network inference to process our response data that shows further improvement. And lastly, with the incorporation of a newer TF binding location data from transposon calling cards or ChIP-XO, we're showing even greater improvement. So with that, I would like to thank my co-authors, Nikhil Patel, Dr. Michael Brent, who's my advisor, Dr. Ravi Mitra, who developed the transposon calling cards assay, and Dr. Scott McIsaac, who developed the ZEV TF induction system. And also I'd like to thank NHGRI and RSG.